We're going to look at section 11.3 here. I forgot to, let's see, float on top. There we go. So now you should be able to see me here. All right, so we're looking at section 11.3. And we are going to talk about what we do when we have two means that are independent. Our two samples are independent and we want to infer about the means. So in section 11.2, looked at when they're dependent or when they're paired data. So if they're independent, they are not paired. We're going to be using our t distribution for this. So in that t distribution, remember that we should have populations that are either normally distributed or we should have a sample size that is at least 30, which is, once again, why in your project you were supposed to have a sample size of at least 30, just in case the populations are not normally distributed for your variables. So we've looked before at our t statistic and where that comes from. So here with these two samples, we're taking a difference between the means. So a difference between the sample means, that's the x bar, a difference between the mu's, the population means, and then on the bottom there, those s's, that's the standard deviations. So pretty ugly formula here. Thankfully, we have StatCrunch to do those calculations for us, because you'd have to do this for both of your samples. You'd have to then find the means and the standard deviations for both of the samples. So again, same requirements as we've been looking at all throughout. The two samples should be done through simple random sampling, not convenient sampling, but simple random sampling. The two samples should be independent of each other for this method. So that means I've got my population. From that, I choose a sample. Then I go and kind of start over. I got my population and I choose another sample. So it's not the paired where it's like, okay, I'm going to choose my sample and now I'm going to choose all of their siblings or something. That would be dependent. So this is completely independent of each other for this method today. We need, again, them to be normally distributed or at least a sample size of 30. But we also need them to not be too big. It's that Goldilocks, not too big but not too small. We can't have our sample be more than 5% of the population. We are going to choose our hypotheses, either that the means are equal, that is our null hypothesis, all the way through, that the means are the same for the two groups, and then what we are assessing is, are they different? Are they either just different, we're not making a guess about which way, or do we have an assumption beforehand about one group having a larger mean than the other group? Choose our alpha level, how confident we want to be that we are not making that type 1 error. Calculate the test statistic, which we'll be doing with StatCrunch. And then we can find our critical value. So critical values come from when we're in a t statistic, we're looking at that chart, and we need to know our degrees of freedom. The degrees of freedom is always one smaller than the sample size. In this independent, the two samples don't have to be the same size, and so then we go with the smaller degrees of freedom. So if one sample has 36 and the other sample has 34, we're going to have 33 degrees of freedom, one smaller than the smaller sample. So once we find our critical value, if it's two-tailed, we have the plus or minus, or one-tailed, only the positive or negative. Then we compare that critical value to our t-value, or we can use the p-value, which is my preferred approach, but some of your homework problems do ask you to find that critical value as well. The p-value relates to that critical value, and it's the area under that part of the curve, the probability that we are in the tails of the curve. So in technology, we have these same slides in pretty much every lesson, so a lot of repetition here. We use technology to find our t and to find the p-value. It doesn't tell us the critical value, so we have to find that from the chart if we need it. And then we state our conclusion. These are robust, which means that if it's not perfectly normal, things are fine. But if we do have outliers, it's risky business to use these methods. So we should check for outliers in our data. Otherwise, if there's a skew to the data or something, it's not perfectly normal, that's okay. But outliers could cause us problems, so we should look for outliers. So, researcher wanted to know whether state quarters had a weight that is more than traditional quarters. So that gives us our hypothesis right there. The researcher believes that the state quarters might have a weight that is more than traditional quarters. So randomly selected 18 state quarters and 16 traditionals and weighed them and got the following data. Okay, so these are independent samples. One big hint that it's independent is that there's a different number of quarters, in this case, in each sample. They cannot be paired then. So in a dependent, we'd have to have exactly the same number because they're paired together. So here, they are independent, different numbers. It could be the same. You could take independent samples that have the same number, but then we would have to ask ourselves the question, did the choice of the state quarters somehow determine the choice of which traditional quarters to use? And it did not. If he was trying to find ones that were like manufactured in the same year or something, then maybe. But these are just, he has a pile of state quarters and he grabs some. He's got a pile of traditional quarters and he grabs some. Okay. So I put that data into StatCrunch. So the first thing we would want to do is to look at a graph of these to see if we have any outliers. So in our graph, I'm going to look at a box plot. I'm going to choose both of those variables, and I prefer to do them horizontally. So I click that button, and I compute, and I look at these, and there's no dots indicating any outliers. So it looks like we're good to go on this. They may or may not be normally distributed. The second one looks a little bit more symmetric than the first one. So possibly the second one, which is, that's actually VAR1 it says. So that is the state quarters. Use more state quarters. The state quarters look like they might be a little bit more symmetric. The traditional quarters a little bit skewed, has a little bit of a pull to the left-hand side there. But it's okay if they're not normal. We just need them to not have outliers. So once we've confirmed that, then we're going to go ahead with our analysis. So I'm going to choose t-stats because I'm talking about a mean here. I have two samples that are not paired up. So I'm just going to choose two sample. So yesterday, last lesson, 11.2, with the dependent, we chose paired. Here, it's just two samples independent of each other. We have data this time. You might have a summary in some problems if it tells you, took these two samples, there was this many in each sample, these were the means, these were the standard deviations, and it just gives you that, then you would choose summary. But we actually have the data here. We know how much every quarter weighed. So we choose data. I'm going to tell it where that data is. And then my hypotheses. The null hypothesis is that there's no difference between them, that the two means are equal. So when I subtract them, I get 0. The researcher believed that the state quarters might be heavier than the traditional quarters. I had the state quarters in column 1. So if column 1 is bigger than column 2, when I do a subtraction of 1 minus 2, I would get something bigger than 0 then, if his hypothesis is true. So then I'm going to compute. And we find our t-stat here. And it's about 2.53. So scrolling through. They did that using the big formula here, 2.53 for the test stat, 2.536, 2.54, so a little bit of a rounding thing there with our t-stat. And then if we wanted to compare that to the critical value, we would need to pull up a t-chart to do that with. The critical value in this case for t is 0.05, because that was our level of significance here, is 1.753, it says. P-value 0.008. So if I'm testing at the 0.05 level, this is smaller than that. So that is then enough evidence to say we have sufficient evidence at the alpha 05 level, or even really the alpha 01 level. There would be enough here to conclude that the state quarters do weigh more than the traditional quarters. So that could then beg the question of how much. So it says the degrees of freedom here. This is the formula for degrees of freedom. So 26.96, that's our degrees of freedom. This is where that came from. That's ugly, right? So it's easier to just go one smaller than the smallest. That will give you a more conservative estimate. This gives us a more realistic estimate, but that would be gross to do by hand, but StatCrunch does it for us right there. So this maybe begs the question, if our conclusion is the state quarters weigh more than the traditional quarters, we might then wonder how much more? Like, am I going to notice a difference in my pocket if I'm carrying around a lot of state quarters instead of a lot of traditional quarters? Like, when a cashier gives me change, should I ask for traditional quarters so that my purse isn't weighed down? Or how big of a difference are we talking here? And that is what confidence intervals can tell us, is an estimate for the difference in those means. So I'm going to go back in and edit this to do a confidence interval. But where does that confidence interval come from? It comes from taking the difference between the two sample means and then adding and subtracting our t value, that critical value, times the standard deviation calculation. Add and subtract that. That's our margin of error when we do this critical value times that standard deviation calculation. That's our margin of error, and that's how much we're adding and subtracting from the mean, or in this case, the difference of the means, since we have two samples. So let's figure out a 95% confidence interval for the difference in the weight. So we concluded those state quarters are probably heavier. How much heavier then? So I'm going to go in and edit this. I have them in var 1 and var 2, so that doesn't need a change, but I am going to change this to a confidence interval at 95%. And make sure, okay, compute that. And here is our upper and lower limits then for our confidence interval. So 0.01 to 0.1, we could round that to. So 0 is not a part of that confidence interval, so that again confirms that there is a difference, okay? And because these are positive values, that it's heavier, the state quarters are heavier. So that confirms what the test told us. If 0 was a part of this interval, then that would mean that there's a chance that there is actually no difference in the weights. But 0 is not a part of this interval. It's really close though. I mean, 0.01 to 0.1. And I think these are measuring in grams. I don't know if it ever actually said. Let's see. Oh yeah, it says in this chart right here that we're measuring in grams. So it is 95% confidence that the state quarters are between 0.01 gram and 0.1 gram heavier. That's not a lot. So I don't think I'm going to notice a difference in my pocket or my purse if I have more state quarters than traditional quarters. So this is one of those situations where we have statistical significance. We do have enough evidence to believe the state quarters are heavier. How much heavier? Not enough to really matter when you're carrying them around. Now, I mean, does it matter for like the US Mint? If they're heavier, that means they're probably using more material. And so as they're making a lot of quarters, is it like costing us more to make these state quarters? How much more would it be costing? We would need some more information on that. How many are they producing and how much does the metal cost and all of that. So, I mean, there could be a practical significance here, but as far as the weight in my pocket is concerned, it's not really a practical significance. So then we have a warning here that talks about what a pooled t statistic is. The idea of a pooled statistic is that you would combine or pool together the data. And it says, caution, don't do that. So right here it says without pooled variances, there's actually a checkbox that it says, do you want to pool the variance? And it's defaulted to be off, and just leave it off. So you probably wouldn't have ever even really noticed that box if I didn't point it out to you, but here's just something saying that the idea of pooled variances is putting the variances together, and we don't want to do that. We want each sample to keep its own variance level. So that's the end of 11.3. As always, ask me whatever questions you have while you're working through this. See you guys later.